Welcome to today's video. Today we're going to focus on a particular kind of solutions to Einstein equations that is going to be particularly important for everything related with orbital mechanics, and it's also going to be important to study objects like black holes. Now, that metric is what I would call the Schwarzschild metric. Now, there's a theorem that I'm going to prove here called Birkhoff theorem. To see a proof of Birkhoff theorem, you can go to Sean Carroll's book, you can go to Wald, you can go to Weinberg's book. Carefully, you go to Weinberg's because he uses the wrong sign convention. Actually, Birkhoff's theorem, it's something that you can prove. It could have been an assignment exercise. I mean, I don't give it to you because it's in every book, but it's something that is pretty easy to actually get. So make an effort to try to read it or make an effort to try to prove it. All right? Anyway, Birkhoff's theorem tells us that the only vacuum solution of Einstein equations, vacuum solution means that are solutions of Einstein equations when the stress energy in areas of space-time where the stress energy density is zero. So in the absence of stress energy density, the only vacuum solution of Einstein equations with spherical symmetry, it's also time translational invariant, and in 3+1D takes the following form that I wrote here. Now, I wrote here the line element, okay, even though oftentimes people would call this the metric. This is the line element, where d omega square is short notation for d theta squared plus sine squared theta d phi squared. Rs is a constant, it's an arbitrary constant, I'm going to call this Schwarzschild radius. It's a radius scale, it's a length scale, right? Now, we're using spherical coordinates for observers at infinity. If you realize why do I call that? Why do I say of observers at infinity, and what do I mean by that? Notice that this spacetime is asymptotically flat. What does that mean? At r going to infinity, this metric becomes the metric of Minkowski spacetime, the flat metric. So this is a spacetime that is asymptotically flat. At r goes to infinity, we have minus dt squared plus dr squared plus r d theta, which is the Minkowski metric in spherical coordinates. So that's when we say that the coordinates t, r, theta, phi correspond to observers that are stationary at infinity. Okay, those are the ones that would have these coordinates as the proper coordinates. Okay, now the coefficients of the metric are easy to determine. Since line element I can write in terms of the coefficients of the metric, I know that GTT, let's have the components to be the 0, 1 would be the t component, the 1, mu equals 1 would be r, mu equals 2 would be theta, mu equals 3 would be phi, okay? So we get that GTT is this one here, is what multiplies dt squared. GRR is what multiplies dr squared. G theta theta is what multiplies d theta squared, which is r squared. And G phi phi is what multiplies d phi squared, which is sine squared plus times r squared. So r squared sine theta squared. This metric is diagonal. You see there are no cross terms. So all the other entries of the metric are 0. All the other components of the metric are 0. One thing to be clear is that this is super powerful because the theorem tells us I don't care what the metric is, but if it's spherically symmetric and in vacuum, so for example, if I have a planet here, I have a planet. Inside the planet, the stress energy density is not 0, but outside of the planet, the stress energy density is 0. So outside of the planet, I don't care what the planet is made of. Outside of the planet, the spacetime has to be of that form, okay? Inside of the planet, it will be different, and perhaps we'll see a little bit about it. In fact, we will see a little bit about it. You'll do an assignment about what happens inside a planet or inside a star, and we will do here an exercise about it. In any case, outside of the planet, if the planet has spherical symmetry, so if the source here is spherically symmetric, then I know that outside, if the whole setup has spherical symmetry, the solution to Einstein equation is going to be something looking like that. Now, what is this Schwarzschild radius? Well, in principle, the theorem doesn't tell us what that Schwarzschild radius is. To find the form of that Schwarzschild radius, what it would be, we need to add extra hypotheses. For example, saying, right, this is the case of spherically symmetric planets, for example, where we have like things, gravitational fields created by spherically symmetric things. So maybe I can find the value of this constant when I'm describing something like a planet. How do I do that? Well, we're gonna do it by matching with Newtonian mechanics in the Newtonian limit. So let's see how we do that. In the particular case where we are far away from the source, so that we are farther away than we're looking at points that are very far away as compared to the Schwarzschild radius. So Schwarzschild radius over the point that we're looking at is much more than 1. Then we can approximate this factor as its series expansion. And as such, I can actually rewrite this metric as this one approximately. Of course, this is at first order plus higher order terms, but if I'm really, really far away, I'm neglecting the higher order terms. This would be the first order approximation to the line element, this thing here. Where this phi, I define it minus 1/2 Schwarzschild radius divided by r. I define it for convenience because we will see how this is a quantity that is going to be relevant when we solve Einstein equations. So we have simplified a lot Schwarzschild metrics because we're really far away from the scale of the Schwarzschild metric, from the Schwarzschild radius. And that far away, it's actually relatively easy. In fact, it's just an exercise in arithmetic. It's a long exercise, but an exercise that is just a lot of very easy arithmetical operations is plugging in this metric into Einstein equations. If we plug it in, what we need to find the Riemann curvature tensor, then the Ricci curvature tensor, then the Ricci scalar. We put all of it into the metric, and for this particular metric, for these particular elements of the metric, the Einstein equations simplify a lot. I'm going to leave it as an exercise. It's just long and it will take up most of the lecture time, but it's a very easy exercise that I really encourage you to do. You plug this into Einstein equations and you get the following. This is what we obtain when we actually substitute these coefficients of the metric into Einstein equations, again computing the Ricci tensor, computing the Ricci scalar, substituting the metric. It simplifies immensely. Notice that there's a 0 here because we're far away from sources, right? Then this equation simplifies to this one. And that's very interesting because that is Laplace equation for this potential phi u1. It reminds us a lot of Newtonian gravity, perhaps. After expanding the metric like this in terms of this phi parameter minus 1/2 rs divided by r, I get Einstein equation to give me Laplace equation. Nice. All right, so let's try to solve that Laplace equation then. Using the fact that this potential has to be spherically symmetric and time independent because of the characteristic of the metric, we are in a spherically symmetric stationary spacetime, then we know the Laplace equation can be simplified to this, where I use the fact that it's spherically symmetric. Now, of course, the solution to that, you've done 1,000 times, the solution is going to be of this dimensionless potential. Remember, this is dimensionless as defined. Is I'm going to write a minus here for convenience. I mean, I could have absorbed the minus into the a constant, but just for convenience, minus a over r plus b. All right, so how do I determine the constants? Well, let's see. I do want to have the Minkowski metric as is for these coordinates are infinity. I want, in other words, to have the origin of potential for this dimensionless potential. I want it to be 0. So what I demand is that phi, this is phi of r, of course, phi of r, and I demand that phi of infinity, r going to infinity, I'm going to say that this thing is going to be 0. And that fixes that b is equal to 0. All right? All right. Now, in order for this potential, we know what it happens with this kind of potentials. We know what kind of gravity it generates. If I want the potential to be an attractive potential, then this A has to be positive, so that this potential is negative. All right? So maybe A is positive. Okay, we got the signature of A. So let's see, A larger than 0. Now, how do we determine A? Well, I want this to be, you see, it should be the case. I really want this to be the Newtonian potential. And why do you mean? Because, well, far away from the gravitational field generated by AMATH, by something spherical, some spherical distribution of stress energy, I know that Newtonian mechanics works. When gravity is, if I'm stationary, far away from the source of gravity, I really want Newtonian physics, Newtonian gravity to work because we've observed it works. So we can match it to Newtonian gravity. In order to do that, I need the potential to be attractive, and I also need this to be proportional. This A, this potential, if you want, has to be proportional to the mass that's generated the gravitational field. All right, demanding that, we obtain that phi has to be equal to minus m divided by r times some constants that has to have the right dimensions to make phi dimensionless. Now, what are the dimensions that it has to have? In natural units, mass has dimensions of length minus 1 over r has dimensions of length minus 1, so that to make this thing dimensionless, alpha has to have dimensions of area. So we need to add a constant, and that yet we don't have any more freedom in the problem. It needs to be a fundamental constant that has units of length to the 2, of an area. Now, do you know any fundamental constant that has that may have units of area? We have seen one when we were practicing natural units. Newton's gravitational constant G has units of area. So indeed, this alpha has to be some proportional factor to G. So you may say, why G and not G over pi or anything like that? How do you know? Because you can add any dimensionless constant to this. Well, I want Einstein equations far away from the Schwarzschild radius to yield something like Newtonian gravity equations for the field. And that implies a Laplace equation for a potential. And because I identify this phi with the Newtonian potential, then I know that this constant has to be G. So if we do this matching, again, this is a matching we're doing. This is not from first principle. This is from saying Newtonian gravity has to work in the weak field approximation when we're far away from the source. Then we find that phi, this phi, where is phi defined here? That is minus 1 over 2 rs over r is equal to minus gm over r. And then if we equate these two expressions, we obtain an expression for the Schwarzschild radius. The Schwarzschild radius is 2gm. Important to realize, the Schwarzschild radius being 2gm is not a fundamental result per se. That's important. The fundamental result is what Birkhoff's theorem tells us, which is that if you are looking for a vacuum solution of Einstein equations that are stationary, time translational invariant, and also spherically symmetric, this is the one parametric family of solutions you would get. What's the Schwarzschild radius? I don't know. That is nothing. In Birkhoff's theorem tells you what Rs is. Now, the way to fix Rs is saying, but I do really want this to be able to describe gravity in a scenario where I have a planet or a star. And I also know that Newtonian mechanics, Newtonian gravity, works really well for the gravitational field of a planet or a star when I'm far away from it at the very least, right? And when I'm stationary with respect to the reference frame at infinity and far away from it. Then from that, you say, okay, yeah, then I'm going to do a weak field expansion on the Schwarzschild metric, getting this, and then I realize when I plug this into Einstein equations that I get the Newtonian Laplace equation. And because of that, I can identify this parameter phi right here, that I define like this, as the Newtonian potential, because it's literally identifying Einstein equations with Newton's equations for the gravitational field. Once I assume that I'm far away from the source, right? And then by matching the two, I find an expression for the Schwarzschild radius. This is the expression for the Schwarzschild radius that will allow you to model a star or a planet in a way that is compatible with Newtonian gravity far away from it. Okay, nice. So that allows me to write Schwarzschild metric as follows, where I have substituted the constant Schwarzschild radius by its value computed by matching the solution with Newtonian gravity far away from the source. Now, notice that this is the Schwarzschild radius in natural units. We can quickly obtain the expression for the Schwarzschild radius in full units just with some dimensional analysis. We know that the units of, let's do it like this, the units of G are length to the power of 3, mass to the power of minus 1, time to the power of minus 2. Therefore, the units of G times M are length times velocity square. So in order to get units of length for the resulting GM factor, I need to divide by c squared. If I do the units of GM over c squared, then I get that thing has units of length only, canceling the velocity ones. So the Schwarzschild radius in full dimensional units is 2GM divided by c squared. So easy. Doing dimensional analysis is how you pass from natural units to chicken Barton units. I store this value here, although we're not going to need it for anything because we're going to be computing all the numbers. We're going to obtain all our results without having to use the full dimensional units. We're going to compute in natural units all the time, but I just leave it there for you to have it. Now, with this Schwarzschild metric, let's analyze it a little bit. The first thing we're going to look for is the existence of possible killing vector fields. They are going to be extremely helpful, extremely useful, and you're going to see it when we do orbital mechanics, but even before that. Now, what are the killing vector fields of this spacetime? Well, just looking it directly in the eye, let me just expand this thing for a sec. Like that, I realize that there are two coordinates that are cyclic, remember? two coordinates that don't show up in the coefficients of the metric. The coefficient of the metric depend definitely on r, depend on theta, one of them, but there are two coordinates on which the coefficients of the metric do not depend. So I know that the translations with respect to time are going to be at isometry because time doesn't show up in the coefficients of the metric. So I know that partial t, let me call it k, this vector, partial t, and also same thing with phi. Phi does not appear in any of the coefficients of the metric. So there's a vector, let me call it s, which is partial phi. These two things are killing vector fields, killing vectors. And this is super useful, and it will be super useful. They're isometries. You see how they are isometries. If I do a time translation that doesn't change, obviously Birkhoff's theorem was for time translation on invariant spacetime, right? So you have spherical symmetry and time translational invariance. And also phi does not show up, and that's related with the spherical symmetry. So these two vector fields are killing fields. We can express them in the coordinates. Remember, I'm going to write here the coordinate vector. I'm going to write here is going to be t r theta phi, just reminding you. So these killing vectors I can write as this. In coordinates t r theta phi. This is the 1, 0, 0, 0, and the other one, partial phi, is 0, 0, 0, 1. Okay, let me store those killing vectors somewhere out of the way, and let's learn a little bit about stationary observers in Schwarzschild spacetime. Alright, I stored here the killing vector fields that are going to be super useful later, and let's now compute what is the time of stationary observers somewhere in the Schwarzschild spacetime as compared to the time of somebody stationary at infinity. So you're very far away, and there's something that is closer to the planet, say even in the on the surface of the planet, and you want to compare how fast your time is as compared to them. Typically, there are two ways to do this calculation. The dirty physicist one, and the proper physicist one if you want, but proper. So I'm going to show you the dirty one first of all, because I'm not going to use the dirty one for the rest of the course, and second of all, because it is used, and it's nice to see it like that, to be prepared for it when you read it in the wild, because you'll see it. This is how people actually do it a lot. So let's do it first, the dirty one. Dirty one starts by saying, okay, I know that d squared is minus d tau squared. Well, you remember it's minus c squared d tau squared, but c is 1 here, where tau is the proper time of an observer somewhere in Schwarzschild spacetime, right? This is writing the line element in terms of the proper time parameter, okay? The next step, this is not dirty, you can do this, no problem. I just wrote it like this, so it's the same line element, only changing the sign, as you can tell. Now the dirty steps come here. They can come in two varieties. Variety number 1, stationary, this is true what I'm going to write, stationary means the following, that I am at r is equal to some capital R, okay? And then theta is equal to some value theta sub 0. Then, I don't know, phi is equal to some value phi sub 0. Alright, so then the dirty one, there are two ways. There's the number one that says, since theta is constant, this is 0. Since phi is constant, this is 0, right? They would just cancel. And then they would say, this is dirty, huh? They would say, since r, theta, phi, constant, then we know that the r equals the theta equals the phi equals 0. Then, being super dirty, and keep saying, I would get that the tau square is equal to, and then we only have the first term because I've cancelled dirtily all the others, and this would be 1 minus 2gm, now evaluated at capital R, which is the value of r, dt squared, okay? And then I would say, alright, so then I know that then the tau it's equal to the square root of 1 minus 2gm divided by capital R dt. I can integrate that, and that gives me that tau, the time of somebody somewhere in Schwarzschild spacetime, stationary, important, so at a given point, stationary there, that person would have to have propulsion, right, unless it's at infinity, because otherwise it's going to fall. That person that is stationary is not geodesic, it's stationary, important, Oh, the only stationary observers that are geodesics are the one on infinity, the ones that got proper time tau, that therefore velocity is the Killing vector partial t. Every other observer that's stationary will not be geodesic. Anyway, so we get that tau, it's equal to the square root of 1 minus 2gm r, just integrating both sides, t plus some synchronization constant. You see that the delta tau, if you have integral serum deltas, right, integrals, so you subtract two of them, delta tau, delta t, this is going to be equal, so delta tau will always be smaller than delta t. So somebody at infinity sees time go slower than somebody that is somewhere else, stationary with propulsion, you can tell already. So I want the for velocity of a person stationary at r, and I know that for velocity is going to be what I call partial tau. Remember, partial tau is the proper time of that person. Partial tau will always be the for velocity of the observer that has tau as proper time. In my own coordinates, my for velocity is always 1, 0, 0, 0, and that is partial tau. All right. Now, partial tau is not 1, 0, 0, 0 in the coordinate that we're using, which is t, r, theta, phi. Then let's find what partial tau is in this coordinate system, right? So the for velocity in general, well, I know it's partial tau, so I'm going to do it, remember, partial tau, it's equal to partial tau, but I can write this using chain rule as partial t, and then dt d tau, okay? Because there's no other variable dependence in this case. And then I get dt d tau I can get from here, you see, is 1 over that square root. So this thing is 1 minus 2gm r to the minus 1/2, all right, times partial t. And there you go. So this is 1 minus 2gm divided by r to the minus 1/2 partial t, which is, I'm going to write here, the Killing vector k. All right. So if I were to express in coordinates u mu, remember u mu is the for velocity of the stationary observer, which in general for velocity, I'm going to write it here. For velocity is dt d tau, dr d tau, d theta d tau, d phi d tau. That's the for velocity. And in this particular case, the for velocity is just 1 minus 2gm divided by r to the minus 1/2, 0, 0, 0, all right? Which is this factor proportional to the Killing vector k. That, remember, is the for velocity for a stationary observer at infinity. And you can tell, if I go to infinity, that becomes just 1. So certainly the two are equal at infinity. All right, with this we could compute time dilation and gravitational Brexit and so on. But this is very, very dirty. This is not the way we're going to do things in this course, although this is the way that is done oftentimes in physics. Now, the way we're actually going to do, there's a semi-dirty thing that is done often, is when you go from here, you say, now I divide everything by d tau square, and then you write something like a 1 here, then d tau square, then d tau square, then d tau square, then d tau square, and it's less dirty in the sense that I don't say the outrageous thing that the differentials are equal to 0. Instead of that, I say, right, these things are equal to 0 because I'm not moving in those directions and so on. So it's a little bit friendlier and yields the same results, right? As I have here. I would have the dt square already here, and then I can integrate both sides, and I end up with this, which again is better if you want, still very dirty. Let's not be that dirty. I mean, we are not, or I am not a pure mathematician, so I'm gonna be dirty by definition, but I can still be less dirty than this. Let's do it a little bit better, shall we? Because that's the way we're gonna be doing it in this course. All right, the less dirty way of doing it is by doing the following. Let's compute for stationary observers. I know that the for velocity of any observer is the derivative of the for position of the observer with respect to tau. So it's the derivative of the t coordinate with respect to tau, the r coordinate with respect to tau, the theta coordinate with respect to tau, the phi coordinate with respect to tau. Now I also know that the for velocity is normalized to -1. All right? So knowing these two things, I can write a normalization condition. I know that -1 it's equal to u, let me just write it, u mu u sub mu, and that is equal to g mu nu, u mu, u nu. All right, so if I do that, I have the coefficient of the metric. This is, remember, this thing is GTT, then this thing is GRR, and this thing is G theta theta, and this thing is G phi phi. All right, so let me just write here the generic one. So I get minus 1 minus 2gm r, then dt d tau square, that comes from the component, the 0th component, or the tt component of this, plus 1 minus 2gm over r minus 1 dr
d tau square plus r square d theta d tau square plus r square sine square theta d phi d tau square.
I know that it's going to be a stationary observer. Remember, stationary observer means that r equals capital R, and then regardless of the values, theta equals constant, then phi equals constant, right? And by doing that, what we know is that theta is not going to change in proper time, with respect to proper time, and phi is not going to change with respect to proper time. Also, r is not going to change with respect to proper time because it's a constant, capital R, so this is going to be 0 in this case. And then the equality that I got is that minus 1 on this, it's equal to minus, and then 1 minus 2gm divided by r dt d tau square. And now we got the same identity, we got dirty. Now less dirty. This is much less dirty, okay? And it's the same identity. All right, I can cancel the minus here, and literally it's the same identity. So we recover the same things we had before. We got the following two things. That the time increase, a difference between a stationary observer and somebody at infinity, it's the difference is given by this factor. This, if you want to call redshift factor, we'll see what we call it that. And that tells you that time, so the delta t is going to be smaller than delta tau. So for an amount of time delta tau, 1 second for somebody at infinity is less than 1 second for somebody somewhere else. And the closer they are to the Schwarzschild radius, the more there would be the difference between them. Okay, you can tell already something funny happens here at the Schwarzschild radius, but we're not going to deal with that now yet, until we get to black holes. Okay, so patience with that. Let's now look into what we call gravitational redshift, which is related with how the energy, the frequency, the wavelength of light, for example, some wave or some photon, if you want to say, is different for different observers that are stationary at different positions in the Schwarzschild metric, because there's a gravitational redshift. So let's see that. To begin with, let's set up the problem. Okay, I'm going to keep these two quantities here that I have. This is, remember, the tau is the proper time of a stationary observer at position capital R, R equals capital R, and u mu is it's for velocity in terms of the Killing vector field, which is the for velocity of somebody at infinity. Now, let's erase this and compute. All right, consider a beam of light for momentum p mu. What is then the energy of the beam of light as measured by the stationary observers at r equal r capital R1 and r equal capital R2. All right, so here we're going to make use for the first time of the Killing equations, remember, from the Killing symmetry. Remember what we derived, something very important at the end of the isometries video? Now, we know that for a geodesic, for velocity mu contracted with the Killing vector mu is constant along the geodesic, all right? Neither of these observers that are stationary are geodesic. Remember, to be in the presence of a planet and not to move, you need propulsion. You cannot stay at the, at zero velocity if you want, stationary at a point and not start falling towards the planet, right? So, for a geodesic, it's true, this is true, but it's not true for the trajectory of these observers. However, it is for light. If I have a beam of light freely propagated, that thing is following geodesics. So it is true that for light, it following geodesics, then we get that p mu, the for momentum of light contracted with the Killing vector field, is constant along the non-geodesic. So this quantity will be conserved along the geodesic. Okay, wonderful. So knowing this, we can easily compute the energy beam of at least the difference in the energy beam as measured at R1 and R2 by two observers stationary at different positions. We know that the energy, as we saw in the special relativity block, is going to be the zeroth component of the form momentum with the index down. It's going to be the conserved quantity associated with invariance and the translation with respect to time. So let's say t in this case, right, the zeroth component. And we know, because the force velocity of any observer in their own frame is 1, 0, 0, 0, we know that to get the p0, p sub 0 component, all that we need to do is the minus contraction of the force velocity of the observer that is measuring the energy with the force momentum of the particle that we want to measure the energy of. All right, so now this force velocity is the force velocity of the observer. Let me write it here. R equals R1, okay? And this p mu is the p mu of the photon. So I'm going to get here minus, and then this factor, 1 minus 2 gm over R1, in this case, to the minus 1/2. And then I'm going to have the killing vector field k mu contracted with the force momentum of the photon. Now, I don't know what this quantity exactly is, but I know that this thing, whatever this is a constant in the whole trajectory of the photon. So if I evaluate this thing at R equals R1, it's going to be the same as R equals anything else, because this thing is actually a constant. This thing is a constant of motion. Constant along the null geodesic that the photon, that the beam of light is traveling on. Okay, so that means that when I write E of R equals R2, I get exactly the same expression. This is PT equals minus U mu R equals R2. Of course, if I want, I can specify this is P mu at R1. Of course, P mu will be changing. P mu will be changing. This is at R2, right? Of course, this is at R1, and the photon at R2 here, right? But what I know is that these factors are 1 minus 2 gm over R2. That changes as well. But this one doesn't. K mu, P mu at R equals R2, it's the same constant. So these two factors, let me just remove the dependence because it's the same value, because it's a constant along the geodesic. Well, that allows me to compute the ratio of the energy of the photon as seen for somebody at R1 and the energy of the photon seen for somebody at R2, which is this. This is what I would call the gravitational redshift of the photon. Somebody at R1 and somebody at R2 would see different energies for the photon, for the beam of light. Therefore, different frequencies, different wavelengths. You can tell, by the way, if you have troubles remembering this is the same thing that we did in special relativity. Go back to two things. Go back to the topic about form momentum, and when we define form momentum out of the Nether's theorem, which remember that the t component of the form momentum is related to the translational invariance of the action with respect to that time parameter, and that is an energy for the observer that has this time as proper time. And we discussed this expression was discussed there. This is just the general relativistic version of it, which is the same. And also you can go back to the exercises we did with form momentum, in which we actually use that to solve exercises. So if you don't remember that, maybe I can show a card somewhere over here that will tell you where you have to go. All right, anyways, so we have this gravitational redshift formula, and you can tell, right? What happens, imagine that R1 is somebody at infinity, and then R2 is somebody at some finite R. So somebody at infinity would have a 1 here, and this thing would be less than 1 for somebody else, right? So you have 1 over something less than 1, larger than 1, but it's the inverse. So that would be smaller than 1. So the energy that somebody at infinity says, it's smaller than the energy that somebody closer to the planet would see. It makes sense, even Newtonianly. A photon needs to climb up the potential, so the energy of the photon will diminish as it's climbing up the potential. So this is the gravitational redshift in general relativity. You can think of this as energies or frequencies. Remember that energies and frequencies are the same. For a photon, you have that the energy change bar omega. Right, if h bar is equal to 1, the energy and the frequency are the same, but even so, the ratio of the energy is the ratio of frequencies. So you have light propagating in the Schwarzschild background. When you see that the surface of a planet, for example, as it climbs up, is being redshifted as it climbs up. And then somebody at infinity sees it with a lower energy, lower frequency. And the opposite, if somebody throws you a photon from far away, then the photon is gaining energy as it's falling towards the planet. You see, the photon is not that it's accelerating in speed, that makes no sense to talk about like that, but it's gaining energy because it's falling through a potential. So of course it's gaining energy as it rolls down the potential. So yeah, a photon gets charged with energy and extracted from the potential that's falling when you throw it from infinity to a planet. In fact, we can take a look at the Newtonian limit. We can take the weak gravity approximation when this factor is very small, which is the Newtonian limit, and then you see that the expansion of this tells you that precisely the energy lost by the photon is the delta of the potential energy that has to cross. So the photon has to climb some potential, and precisely the difference in energy of the photon is the difference in the potential that it had to climb. All right? I just wanted to show you this before moving to gravitational time dilation. All right, so here's the difference. Using this expression, the expression we had here, we know that the difference between the proper time of an observer at a given radial position that is stationary, that has propulsion staying there, stationary, and the proper time of somebody stationary at infinity is this factor that allows me to relate the proper time of two stationary observers at radius r1 and r2. Now, the redshift factor between them is this one here, this square root that I have here. Now, this allows me to compute gravitational time dilation. For example, how much different is if I'm stationary on the surface of Earth, how much different is my time from somebody who's stationary at a geostationary orbit, for example. Now, keep in mind that a satellite is not stationary. A satellite is actually falling geodesics, right? It's free falling in a way. So this is not going to be the time dilation we get with the GPS clocks, right? But it's what the time dilation that we would get if the GPS clocks were actually stationary. You know how the GPS system works, right? And you know GPS is the first technological application of general relativity. GPS would not work without general relativity. Quick introduction on how the GPS system works. The GPS system is, simplifying a lot, a bunch of satellites with clocks, with really precise clocks. And the clocks are synchronized, and the clocks are broadcasting the time. So when I have a GPS receiver, I'm receiving the time from several satellites. Now the principle is simple. Some satellites will be far away from me, some others will be, because they were like far on the horizon, some of them will be right on top of me. The ones that are on top of me are closer. So the signal takes shorter time to get to me than from the one that is far away all the way there in the horizon. So that means that because they identify themselves and they tell me the time, I receive one time and then another time from another with a delay, and I know, oh, okay, the delay, because the clocks are synchronized, the delays are just because of the fact that one of them is larger than the other and the signal took longer to propagate to me. That'll be all cool. And then if that's the case, I can, because I know the speed of light, I can know the distance to the satellites, and therefore I can know, because I know where satellites are where, I can triangulate my position on Earth. That would be great. The only problem is that the time here on Earth and the time on the satellites is actually very different. Well, not very different. It's actually slightly different from each other because of from general relativistic effects. So we need to correct for those general relativistic effects. So we need general relativistic calculations of redshift factors of time dilation to correct for those differences. Otherwise, the precision of the GPS cannot get below 10 meters. To get below 10 meters, we need to correct for general relativistic effects, because it's so precise, the estimation of time that we need to triangulate the position of the satellites, or our position with respect to them. All right, knowing that, let's compute the gravitational redshift. Let's a particular case of a calculation of the gravitational redshift between the surface of Earth and somebody stationary at the geostationary orbit. Remember, stationary, that won't be the satellite, but it will give you some effect, some gravitational effects between the two. Let's lay out the parameters. So this is the data, this is the radius of Earth, this is the geostationary orbit, this is the radius of the geostationary orbit, this is the mass of Earth, this is Newton's gravitational constant. But of course, we want to compute in natural units, which is where we have these expressions. So let's convert into natural units, or your favorite thing. For example, natural units of length, all of them. All right, the radiuses are already natural units of length, meters. Mass I transform to meters minus 1, which gives me this, which is the inverse Compton wavelength of Earth. And the gravitational constant in units of area, it's this quantity, which is actually the Planck area. All right. If we substitute, this conversion we've actually done in the first lecture on general relativity, in case you don't remember. Anyway, we're going to compute this factor. So if we plug the numbers in, we get the following numerical factor. So delta tau 2 divided by delta tau 1 is 1 minus 5.9 10 to the minus 10. So basically, per each second of time here on Earth, the satellites delay by half of a nanosecond. Well, the satellite, somebody stationary at the position of the geostationary satellites would delay half a nanosecond. Now, for the realistic satellites moving like that, it's more like a full nanosecond action. It's more like a full nanosecond what it delays. By the way, common misconception. You will often hear, and that's because there are engineers that use those formulas, you will often hear that for the GPS in popular science, you need to add, oh yeah, you need a special relativistic correction because the satellite is moving with respect to us, and also a general relativistic correction because of gravity, the kind of thing that we have just done here. That is utter outrageous. No. You can, in general relativity, you cannot separate between the two easily. By that I mean, no. In general relativity, you cannot separate these two things easily. In fact, it's called general relativity because you do not need to compute separately something special relativistic or something general relativistic. No, there is only one relativistic correction, and you don't disentangle them between, if you want, velocity effects or whatever you want to call that, and gravity effects. That is utter nonsense conceptually. Now, it is true that for weak gravity, you can write a series expansion for weak gravity and get a term that looks a lot like something special relativistic plus a term like this. And that's why the engineers say, oh yeah, this is the special relativistic one, this is general relativistic one. Okay, fair enough, within the realms of that approximation, you can kind of separate, but never think that you would have, that actually induces people to think that they have to compute special relativistic corrections and then general relativistic corrections, and that makes no sense. We will see that way more in detail when we talk about the orbital mechanics in general relativity, okay? But just wanted to say. Now, before moving precisely to orbital mechanics, one more thing. What do we call weak gravity? And can we talk about weak gravity in the solar system? Is that weak gravity enough or not? Well, actually, we can estimate with the value of the potential phi and we saw that we get the Newtonian approximation when this parameter is small, right? Now, one can think what this value would be for different astrophysical scenarios. For example, the surface of Earth is 10 to the minus 9, so you can say, yeah, Newtonian gravity may work well for the surface of Earth, doing a first order approximation in which I consider only the Newtonian contribution. Actually kind of a leading order approximation, I don't want to even call it first order. Then on the surface of the Sun, this parameter is 10 to the minus 6, so it's still pretty good. On the surface of a solar mass neutron star in 10 to the minus 1, so probably you shouldn't do that approximation, as we know, very relativistic there. But even at this level, right, we see that GPS requires corrections, and also that we're gonna get the orbits of the planets require corrections in order to match astronomical observations. We're gonna do the problem of the precession of the perihelion of Mercury. That is the first falsifiability test of Einstein's theory of relativity. All right, this is as much as I want to tell you in this video. We're gonna end here, and in the next video we're gonna learn orbital mechanics in general relativity, to be compared with orbital mechanics in Newtonian gravity. All right, I'll see you in the next video, and until then, take care.